Hi, I hope that you are doing great. This is the fourth video that I am going to talk about yet another method of factoring polynomials. But before starting today's lesson, I think mentioning some points is in order. If you are following my YouTube channel, you probably know that there is a playlist on my YouTube channel called Advanced High School Algebra. This video is uploaded onto that playlist, and in the descriptions below the video you will find 5 links. The first link, as is common to the videos of this playlist, and you might already know it, gives you access to a PDF file containing a number of problems including the final answers, of course if applicable. As you might know, the next video that I will upload nearly 1 week from now will be a video that I will present and discuss all the detailed solutions to the problems of this file. From my point of view, there is only one way to learn mathematics, and that is to do mathematics through solving more and more problems. The problems of this PDF file are partitioned into 2 groups. The first group contains the problems that are directly related to the material that I will cover in this very video. Of course, the primary goal of these problems is to help you improve your understanding, skills, and problem-solving strategies on the material that you will learn in this video. The second group contains problems that take your knowledge from the previous lectures as well as might be this lecture for granted. Usually, I select harder and more challenging problems to be in this group. I have several reasons for that. Firstly, because a hard problem is more fun than a simple problem, and even though solving it entails hard work and commitment, but at the end it will bring you a lot more enjoyment and satisfaction if you could solve it, or more experience if you could not solve it. My second reason is that this is the second round that you are dealing with problems related to the previous lectures, and you have now more experience, and in principle you are capable of tackling harder problems on the subject now. Finally, to succeed to solve a hard problem, you have to be extremely focused and spend more number of hours on the problem. Yes? Sometimes you might need to go back, review your notes, watch back some parts of the previous videos, or even you might need to Google around and see what you can find on the web that can help you solve the problem. All these make you be really engaged with the problem for more number of hours, and of course in reward you will have the chance to transfer most of your math knowledge, and especially handy formulas, from your short-term memory to your long-term memory, and use them in your future university studies or your future career, if it is related to mathematics in somehow. But what about second link? The second link is the link to the PDF file of these notes that you right now see on your display, and I am moving it. And in this lecture, I will write down my explanations in between the empty spaces, for example here, and if I go to the next page here, that I have already provided in the file. In this file, the solutions to the examples that I will present in this video are not, of course, included. By the way, I use iPad Pro together with Apple Pencil and GoodNotes 5 application to produce these videos. The content of the third link is exactly the same as the second one, except that this one is the GoodNotes version of the file. I strongly recommend you to have one of these files available when watching the video. If you have access to a tablet with GoodNotes installed on it, then you can use the third link to download these lecture notes directly onto your tablet, as if you yourself have created them in the first place. Otherwise, you can use the second link to download a PDF version of these files, of these notes, and print them. I think having the notes in front of you while watching the video could be helpful, very helpful in active learning. And finally, the fourth and fifth links are links to PDF and GoodNotes files accordingly of exactly the same lecture notes, but this time the files include my detailed solutions and explanations about the problems, about the examples and the, I don't know, theorems, remarks, etc., etc. Okay? So I think I mentioned everything that I needed to mention. Now I think we can start the lecture now. Okay, so as I told you in the beginning, in this video I am going to teach you another method for factoring a polynomial. And I want to teach you how the long division will help us to factorize a polynomial more effectively. If you have following the lectures, the previous two lectures especially, you might have seen that is sometimes to factorize a polynomial, one needs to break one or more terms of a polynomial and write them as a sum or difference of two or more suitable terms. And then use the grouping trick to the new form of the polynomial and try to factorize it. Of course, finding suitable terms to break the terms into might be extremely out of reach, counterintuitive, intractable, even if you are really experienced. It's not easy to guess or to see the strategy to find suitable terms. On the other hand, there are some cases that somehow we have access to at least one root of the polynomial that we are supposed to factorize. In these type of problems, long division of polynomials will come and help us. And you will see that we really don't need to be very observant or very smart to be able to guess those suitable terms that we want to break the terms of the polynomial into them. Okay, but you might, of course, this is a little bit of deficiency of this method. Somehow you need to have some kind of knowledge about at least one root of the polynomial. I agree with you, but then I will present you two theorems that somehow we can circumvent this deficiency. Okay, but before that, let me try to explain why this method is going to work in the first place. This is the idea. The idea behind why this method that I'm going to explain will work is a theorem about polynomials. What is the theorem? The theorem tells you that if you have a polynomial p of x, and you know that p calculated at x0 is equal to 0, namely if x0 is a root of your polynomial, then that theorem, as we saw when I was teaching you polynomials, about polynomials, P of x is divisible by x minus x0. Okay? So take this for granted. So if you want, I can write it here. So let me write it here for you. If P of x is 0, this implies that P of x is divisible by x minus that number. So this is a very important fact that you need to know. Okay. Okay, now let us solve a very simple problem. I will explain everything in this problem. So let me read it for you. Consider the polynomial p of x equals to x to the 3 minus 7x minus 6. We first want to show that minus 1 is a root of this polynomial. Of course, in this problem, the problem itself has introduced a root, proposed a root to us. Our duty is to confirm that this is indeed a root. But of course, you know that this is a very, very simple task. What I need to do, I need to calculate p of minus 1 and confirm that p of minus 1 is equal to 0. So I calculate p of minus 1. How? I replace x's everywhere with minus 1. Minus 1 to the 3 is minus 1 plus 7 and then minus 6, which is exactly 0. So therefore minus 1 is a root of p of x. Yes. Now use part 1 and long division method to factorize p of x. Okay, so I want to do the long division method to factorize my polynomial. So let me show you this again. I want to use this fact. So we learned that p minus 1 is 0. So according to this, what can I conclude? I can conclude that p of x is divisible by x minus x0. What is x0 here? This is my x0. So this becomes x minus minus 1, yes? Which is x plus 1. Yes? So we realize that p of x is divisible by x plus 1. Then I use the long division method to find the quotient of the division of p of x by x plus 1. I am not interested in the remainder. I already know that. I trust this theorem. I already know that the remainder of the division of p of x by x plus 1 is really 0. What I am interested here now is find the quotient of this division. Okay, so because we have enough experience of doing the long division, so let me just do it quickly here for you. So what I do, I would write x to the 3 minus 7x minus 6, and then what can I do? And I would write it in this form. Yes, so I would write x plus 1 here, and I start dividing these two polynomials using the long division. So the first term divided by the first term is x squared, and I put it here, and then I multiply it here. It becomes x to the 3 plus x to the 2. But what I am doing, I am going to write this and subtract these from that. But when I put minus sign here, it means that I need to be careful. This becomes negative, this becomes negative, and then I will add them. So to keep track of that, I put a negative sign here and a negative sign here, and then I add them instead of subtracting them. So then you will see that this term and that term are gone, and then I will have a minus x squared coming first, minus 7x coming second, and minus 6. And then I repeat the process once more, yes? So I will multiply, I will divide minus x squared by x, it becomes minus x. Then I will multiply, it becomes negative x squared, negative x. Then I will change the signs, positive, positive. and then I add them. So then it becomes minus 6x minus 6, yes, and then I divide it once more. So what will happen is minus 6. It becomes minus 6x minus 6, and then I will change the sign so it becomes positive positive, and I add them together, and finally it becomes 0. Yes, so when it becomes 0, I can write this immediately. I would say that the divisor multiplied by the quotient plus the remainder will give me the dividend. Okay, so what does it mean? It means the dividend that I am going to factorize it is equal to x plus 1 multiplied by x squared minus x minus 6 plus 0. But of course nobody writes plus 0, so let me clean it. And when I clean it, look what happens. You have your polynomial in a product form. So it means that you already succeeded at least to partially factorize your polynomial. Why I say partially? Because now you have enough experience of factorizing these quadratic polynomials, and you immediately realize that this can be factorized even more. So I will open two pairs of brackets, put x here and there, and then I will ask myself, I need two numbers whose sum is -1 and whose product is -6, and that is extremely simple to guess. Yes, that's -3 and then +2. Yes, and then look what happens. If you see here and here, you see that this expression is fully factorized. So you see that how this extra piece of information actually helped us to factorize this polynomial. Okay, to compare it with what we learned before, this is why I have mentioned the third part for this problem. Can you factorize this polynomial without needing to know that -1 is a root of this equation? If so, how? Of course, this is easy, so we don't need to struggle a lot, but I would say that this is not that trivial. So let me try to solve part 3 together. Hopefully you have enough experience by now. So this is part 2 of the problem, and let us go to part 3 of the problem. So what was my polynomial? My polynomial is x to the 3 minus 7x minus 6. Yes, that was my polynomial. But then you need to be a little bit here smart and experienced. This problem at this level probably is not that hard for me. But if you increase the number of terms in the polynomials, realizing that how should I break the terms is really challenging. Okay, but here I can write it in this form. I can write x3 instead of minus 7x. I break it into two parts, one of them minus x and the other one minus 6x, and then I have minus 6. Of course, I have some experience from the previous problems, but I told you, let me emphasize again, it's not easy at all. Okay, so what can I do now? I can continue. I can take these two in one group, and I can take these two in the same group. In the first group, I factor x out, so x squared minus 1 is left. And in the second one, I can factor minus 6 out, x plus 1 is left. This seems to be an unsuccessful grouping because there is no common factor produced yet, but immediately you have a lot of experience now. X squared minus 1 can be further factorized, yes. So it becomes x plus 1 and x minus 1, and then I have minus 6x plus 1. And then you see now the common factor that I was looking for is now emerging. So I can pull it out. So when I pull x plus 1 out, what happens? X plus 1 is gone out, so x times x minus 1 is left. So x times x minus 1 is left, and then from the second one minus 6 is left. So, and if you see, I can multiply the second term because I told you nobody will leave this term in this form. We simplify it and remove the extra brackets. So it becomes x squared minus x minus 6. And now if you compare this one, this is exactly that one. And of course you can continue. You can go and write x plus 1, x minus 3, x plus 2. Yes? But look, as you see, in the long division method, I am just following a set of rules. I am not guessing at all. Of course, it might be a little bit longer. But if you are actually smart enough to be able to find the suitable terms, then of course it's a little bit easier to write. I don't know. But of course, finding these suitable terms, especially when the number of terms in the polynomial is really high, is not easy to detect at all, even for experienced people. Okay? So, I hope that you somehow learn. But the deficiency of this method, I agree. So far, the deficiency of this long division method to factorize a polynomial is that, of course, you need to have an extra information regarding the roots, or you need to have at least one root of your polynomial. And I will tell you about the theorems that somehow you can use them to actually remove this deficiency in some ways. Okay? So hopefully you'll learn this one, and then we now go to the next page. By the way, before leaving this page, let me draw your attention to some very interesting point. I'm teaching you a very nice trick. You see here, if I wanted to solve the problem in this way, I realized that I have to break the middle term minus 7x to minus x minus 6x. Look here. These minus x and minus 6x below the minus 7x are actually appeared actually in this process. So okay, so remember this. I will come back to this point later. Okay. So we realize that this is the weakness of this method, and I go to the next page now. And now that is the theorem that I promised you. Okay? So this theorem will help us to be able to somehow guess that extra piece of information which in the previous problem was provided by the problem itself. Okay? So let me read this theorem for you. Let p of x be a polynomial with integer coefficients. So it means that this is a polynomial. These coefficients that you see here, all of these coefficients are considered to be integers. If you have a polynomial of this type, this theorem only works for this type of polynomials. If an integer number m is a root of this polynomial, then m is a factor of this constant term a0. Okay? So, let us prove this theorem first. So let me write the proof for you here. So, proof. What we know? We know that m is an integer. We also know that m is a root of p of x. So what does it mean? It means that p of m is equal to 0. Yes? But what is the meaning of p of m? It means that I need to go to my p of x and I have to replace every x that I see here with number m. And then the result is supposed to be equal to 0. So let me do that. This implies that, let me write here, an m to power n plus a sub n minus 1 m to power n minus 1 plus a n sub n minus 2 m to power n minus 2, and I will continue and I will write a2 m to the 2 a sub 1 m plus a0 is equal to 0. Okay? Now see, all the terms that you see here, from here up to here, share a factor of m. Okay? I can pull one m out from all these terms, yes? So what happens? I will have m, I factor m out between these terms, only these terms. Yes, then what is left for me? It becomes an m to power n minus 1 plus a sub n minus 1 m to power n minus 2 plus a sub n minus 2 m to power n minus 3, and I will continue and I will reach to a2 m plus a1, and then I'll have plus a0 equals to 0. Now look, this number m here is an integer according to this assumption. All these factors that you see here are integers based on this assumption. Yes? And now you know that because this p of x is supposed to be a polynomial, n is a natural number actually. Yes? So this means that this combination, even though written in a complicated form, but at the end of the day it's an integer. Yes? This is an integer, this is an integer, everything here is integer, and then I am multiplying integers, raising integers to powers and adding them together. How complicated it is, I don't care, it becomes an integer at the end, so let me call that integer k. So I will call this integer to be k. So then what happens? Then it means that I have m times k plus a0 equals to 0. What is k? I don't know. What I know is that k is an integer. That's the only thing that I know. Okay, then what happens? This means that a0 is equal to minus mk. Instead of minus mk, I can write positive m multiplied by minus k. They are exactly the same thing. But of course, look, if k is an integer, it's completely clear that minus k is also an integer. And now what I have? I have an integer multiplied by m, it becomes equal to a0. So it means that m itself is a factor of a0. Yes? So this immediately tells me that a0, m is a factor of a0. And that is the end for the proof of this. So the proof was very, very simple. Yes? Okay, so let me repeat. It tells you that if an integer is a root of a polynomial, that integer should be a factor of the constant term of the polynomial. Okay, based on my experience, let me give you this remark. I want to make sure that you do not misunderstand the problem, the theorem. The theorem does not claim that any factor of a0 is necessarily a root. Yes? For example, consider this polynomial. X squared 3x plus 6. The coefficients are all integers, 1, 3, and 6. What this theorem claims is that if this polynomial is supposed to have an integer root, that integer root should be a factor of this constant term. What does it mean? The constant term 6, what are the factors for 6? Plus or minus 1, plus or minus 2, plus or minus 3, and finally plus or minus 6. These are the only integers that 6 is divisible by. Okay, these are the only possible integers that might be a root of this polynomial. But of course, in this case, if you go and test them, none of them is a root. For example, if I take plus 1, put it here, it becomes 1 plus 3 plus 6, it is not 0. If I put minus 1 here, it becomes 1 minus 3 plus 6, it is not 0. And you can convince yourself for the other numbers. So this theorem, you see, this theorem doesn't guarantee that the factors of 6 are roots. And you see, this is not the case. But it tells you that if this polynomial is going to have an integer root, where to look for them? They are among these numbers. If you cannot find any number among these numbers that satisfies the equation, so it means that this polynomial doesn't have any integer roots. Okay. So let me just explain it here. Therefore, a possible way to determine integer roots, if any, there is no guarantee that we have integer roots, of a polynomial like this, is that we go and find all integer factors of a0 and start checking them one by one into the polynomial. If you get 0, this means that that integer number is a root. If not, if you finish the list, if you finish checking the list of factors of a0 and you don't get any roots, it means that the polynomial doesn't have any integer roots at all. Okay? Of course, it still might have a root on Q or R, on the set of rational numbers or on the set of real numbers. And of course, it will definitely have a root on the set of complex numbers. This theorem is actually very helpful in factoring polynomials, because if you remember, I told you that by default, what we do, we try to factorize a polynomial on the set of integers. So this is why this theorem is helpful actually, because you see that we are dealing with integer factors here. Okay, so now hopefully that you learned what is going on. So we more or less don't need that extra piece of information provided for us by the problem itself. If we want to find integer roots, and if we are lucky that that polynomial has indeed an integer root, we know where to look for it. We go and find the factors of the constant term and then try to fit those numbers into the polynomial and see that which one will work for us. Okay? Now I want to use this theorem in another example on the next page. Okay, so let us go to the next page. So I want to solve a problem using this theorem. Okay, so this is my example. Use the theorem 15.3, that was the same theorem I mentioned in the previous page, to factorize this polynomial. And then can you factorize this polynomial without using this theorem? If so, how? Okay, we will come to that later. So here I want to factorize this polynomial. Okay, let me write it down here. X to the 3 plus 6x squared plus 11x plus 6. Of course, one way is to be creative and try to see how should I break these terms into suitable terms so that I can factor successfully this polynomial. But of course here I don't want to use that. I want to use this theorem. Okay, first of all, this is a polynomial with integer coefficients: 6, 11, 6, and 1. All of them are integers. So the previous theorem is actually applicable. If this polynomial is going to have an integer root, that root should be among the factors of positive 6 here. So what are the factors of positive 6? Factors of 6 are plus or minus 1, okay, plus or minus 2, plus or minus 3, and finally plus or minus 6. So I have 8 numbers in my list. I start checking them one by one. As soon as one of them works, that is my root. Then I can immediately use the long division process to factorize my polynomial. But if my list ends and I cannot find any root in this list, it means that this polynomial doesn't have any integer roots. Then on the next pages I will come back to see if we still can factorize the polynomial or not. Okay, so this is more or less a boring task, but of course this is doable. You see, this is in practice possible. I have this list and then I need to go through all these numbers to check them, and it is possible, even though it might be tedious. So I put 1 there. So then what happens? By the way, I don't need to check the positive ones, you see, because the signs are all positive. If I choose a positive sign, so then this number definitely becomes positive, but my goal is to make it equal to 0. So forget about the positive signs. Positive signs for this case does not work. Let me start with the negative one. So let us see. I put negative 1 here, so it becomes negative 1 to the power of 3 plus 6 times negative 1 to the power of 2 plus 11 times negative 1, and then I will have, so by the way, let me call it p of x. So this is p of minus 1. Yes, so then it becomes plus 6, and let me calculate this. This becomes minus 1, positive 6, minus 11, positive 6. Indeed, this becomes 0. So I don't need to go any further, yes? So I found the root. P of minus 1 is equal to 0. So according to the theorem that I mentioned on the first page, P of x is divisible by x minus minus 1, which is x plus 1. Yes? So then it means that if I use the long division to divide this will work. So let me just do it here. So I would write x to the 3 plus 6x to the 2 plus 11x and then plus 6, and then I divide this by x plus 1, and I do the long division. So let us do it. Okay, so I divide the first term, it becomes x squared. I multiply, it becomes x to the 3 plus x to the 2, and then I will change the signs, and then I will add them. So these two terms are cancelled, and this minus x squared and 6x squared becomes 5x squared, and I will bring down 11x and plus 6, and I continue the process. So the next term would be 5x. If I multiply, it becomes 5x squared plus 5x. Okay, and then I will change the sign here to negative and to negative here. I put the opposite sign here, yes. So then I add them. This one and that one are gone. Minus 5x and 11x are added to 6x, and then I will have 6. And as I expected, the remainder becomes indeed 0. If I multiply it, it becomes 6x plus 6, and I will change the signs, and then I will add them. This becomes 0. Yes. And then finally, I would write that the dividend, which is my polynomial, is equal to the divisor multiplied by the quotient plus the remainder. But because the remainder is 0, we have my polynomial in factorized form, which was my goal indeed, yes? So what I do is this. I would write my polynomial x to the 3 plus 6x squared plus 11x plus 6 is equal to the divisor multiplied by the quotient. Yes? Plus the remainder, but of course the remainder doesn't have any role here. So you see, this is in the factorized form without actually being so creative, you know. I wasn't creative at all. I just found the factors of 6 and tried to test them one by one. I realized that the positive signs, there is no point for them because all of the signs are positive. I will not be able to get 0 back from these positive numbers. And then I was lucky, the first one that I checked worked. If it doesn't work, I will go to the next one. Yes, it doesn't work, I go to the next one. Okay, so you see, even though this is lengthy, but it is not based on guess. Okay, so I was able to do it. Of course, you have a lot of experience now. Now that you see that this is not finished yet, I can factor it a little bit more. X squared plus 5x plus 6 can be written. I open two pairs of brackets, put x in each one of them, and I ask myself, I need two numbers whose sum is positive 5 and the product is 6, so I will write positive 2 and positive 3 here. So this is the fully factorized form of my polynomial. Now let us go to the next one. In the previous lecture, if you have watched the video, if I give you this, my goal is not you to use this. I want you to see that if you can break these terms, all the terms, in a way that you can factorize. And I think that this is not easy at all, but let me try to do this in another way. Assume that this is the previous lecture and you want to do it based on the previous lecture. Okay, so you would write x to the 3 plus 6x squared plus 11x plus 6. So what I need you to do is to write x to the power of 3 and then you, instead of 6x squared, you would write 5x squared plus x squared. Yes, and for the 11x squared, you would write 5x plus 6x, and instead of 6, you write 6. Of course, you see, this method is simpler, but finding these breaking terms is hard. How should I know that I need to break 11x into exactly this form? Because 11x can be broken into two parts in infinitely many ways. But why on earth I should have chosen this and that one for these terms? But first of all, you need to be patient and see that this will work. Yes, so I will take this one with that one. I will group these two together, and I will group these two together. Yes, so then what happens? I factor x squared from the first one, it gives me x plus 1. I factor 5x from the second group, it gives me again x plus 1. And finally I factor 6 out from the third group, it gives me x plus 1. So this is indeed successful. Yes. And then you see immediately I can factor it out. It becomes x squared plus 5x plus 6. And then as you know it, immediately you can write x plus 2, x plus 3. Yes. Okay, I am not saying that this is not shorter. Indeed, this is shorter than the previous method. But look, guessing these numbers are not easy. Okay, but now look, I want to teach you a trick here. Actually, how I realize that I need to do it, I have this long division in front of my eyes. I cheated a little bit actually. These breaking terms actually appears in this long process. You see, here I have 6x squared, which is this middle term, and then you see that I have positive x squared and 5x squared here. So this is why I immediately realized that I should write 6x squared as a sum of x squared plus 5 squared. And look, what about 11x? 11x is this term. It's already here for me. You see 5x and 6x. So I really did this immediately using this. Otherwise, if this was not in front of my eyes, I was not able to do it so quickly as I did it right now. Okay? So I hope that you understood that this method is indeed useful. Okay? Okay, so yeah, I think one example is not enough for this. So let me go and look at another example, okay? Okay, so let us go and solve one more problem here. Factorize polynomial px equals to this. Okay, so again, you see that I don't have any extra piece of information here. I will go here. First of all, is the previous theorem applicable to this polynomial? I would say yes. Why? Because I have these are integers. Yes, the coefficients are all integers. So what I need to do, my minus 24 is my constant term. So what are the integer factors of minus 24? Of course, plus and minus 1 is always in the list, and then I will have plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, plus and minus 8, plus and minus 12, and finally plus and minus 24. Of course, I have a very large list here, but this is the way that we can do it. But I hope that you can appreciate that solving this one is really hard, because I have more terms here and the numbers are more involved. Yes. So I would say that there is no chance to come to the appropriate terms, that we have to break the terms into those terms. Okay, so what I do, I start doing the list here. So for example, if I put minus 1, so let us check. If I put 1 here, it becomes 2 times 2 plus 7 minus 17, and then minus 58 minus 24, which is clearly not equal to 0. And then I put minus 1. If I put minus 1 instead of x everywhere, the first one becomes 2. The next one becomes minus 7, minus 17, positive 58, minus 24. As you see, it's minus 5 minus 22. It's not again equal to 0. Yes. Let us go, for example, to 2. If I put 2 here, then it becomes 2 times 2 to the 4 plus 7 times 2 to the 3 minus 17 times 2 to the 2 minus 58 times 2 minus 24. So then this becomes 32 plus 56 minus 68 minus 116, and then I will have minus 24. But again, this is not equal to 0. I go to the next number, minus 2 this time. So I put minus 2. Then I will get 2 times minus 2 to the 2 plus 7 times minus 2 to the 3 minus 17 times minus 2 to the 2 minus 58 times minus 2 minus 24. So let me calculate it exactly in front of it. So oh, sorry, this is not 2. This is this is 4. This is 4. Yes, because the power here is 4. Okay, and then what happens? It becomes positive 32 again, and then minus 56, and then minus 68, positive 116, and minus 24. Yes. So what happens here now? It's minus 80 minus 100. So this is 0. Yes. Let me double check. So this is minus 80 minus 148. Yes, exactly. That's 0. So you see, I realize that minus 2 is a root of this polynomial. So I would say that p of minus 2 is equal to 0. So what can I conclude? I can conclude that p of x is divisible by x minus minus 2, which is x plus 2. Okay? So what can I do now? I can do the long division process. So I would write 2 x to the 4 plus 7x to the 3 minus 17x to the 2 minus 58x minus 24. Then I will write it, let me make it more nicely. So here I will have x plus 2, and I do the long division. Okay, so the first one is 2x to the 3, so it becomes 2x to the 4 plus 4x to the 3. I will change the signs, negative, negative, and then I will add them. So the answer becomes it becomes 3x3, and then I will have minus 17x to the 2 minus 58x and minus 24. Yes, so I will continue the process. So I will have plus 3x squared, then it becomes 3x cubed, plus 6x squared, then I will change the signs, negative and negative, and then I add them, this gone, and this becomes minus 23x squared minus 58x minus 24, and then I continue here. It's minus 23x. I multiply it here, it becomes minus 23x squared, and then I have minus 46x. I will change the signs, positive and positive, and I add them. This is gone, then I will get negative 12x minus 24. And finally, I would write minus 12 here. It becomes negative 20x, negative 24. I will change the signs, positive, positive, and then I will add them as I expected. The answer becomes 0. Yes. But now what should I do? I can write this expression. I would write that the divisor multiplied by the quotient plus the remainder is supposed to be equal to this. Yes. So what I get is that 2x to the 4 plus 7x to the 3 minus 17x to the 2 minus 58x minus 24 is equal to x plus 2 multiplied by 2x to the 3 plus 3x to the 2 minus 23x minus 12. Okay, so I have already written it in the factorized form, but it is probably not fully factorized. The bad news is that this factor is again another polynomial which is not probably that easy to factorize. We need to use the same method this time for this polynomial. Yes, so keep it here. So let me keep this here. I will need it. But let me now go and then try to do the same thing here. This time, the constant term here is minus 12. So I would write minus 12 and I will list the factors. They are plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, and finally plus and minus 12. Yes. So for example, we need to check them again one by one. For example, 1 and minus 1 are clear. If I put 1 instead of x everywhere, it's clearly not equal to 0. If I put minus 1, again, this is not clearly This is not 0 again. You see, this becomes positive 23. Yes, this is not again 0. If I put 2 positive 2 here, what happens? If I put positive 2, it becomes minus 46, minus 58. This is, yeah, it is not 0. If I put negative 2, then this becomes very positive. It's not still the case. Now I go to the next number, positive 3. Okay, let me check them. If I put positive 3, so I will get to 3 to the 3 plus 3 times 3 to the 2 minus 23 times 3 minus 12. If I calculate this, it becomes 54. The first one is 54. The second one is 27. And then minus 69 minus 12. Yes, so this is minus 81. This is 81. Yes, so this is 0. So if I put positives 3, it is 0. So let me double check again if I have made any mistakes. So I put 3 here. So this is 54 and this is 27. So far this is 81. And then I have minus 69 minus 20. This is minus 81, and that is again equal to a 0. So 3 is actually indeed an answer. Okay, so let me call this one qx. So let me call this to be a new polynomial qx. So I realize that q of 3 is equal to 0, so this implies that q of x is divisible by qx is divisible by x minus 3. So what I do, I again write qx, which is 2x to the 3 plus 3x squared minus 23x minus 12, and then I did divide it by x minus 3, and then let us see how it goes. I divide 2x3 by x, it becomes 2x squared, so I multiply it, it becomes 2x3 minus 6x squared. I will change the signs, and then I will have this one and that one are gone. I will get 9x squared minus 23x and minus 12. I repeat the process, it becomes positive 9x. I multiply it here, 9x minus 27x. I will change the signs, negative, positive. I add them, this is gone. I will get 4x. Yes, so I will get 4x minus 12. And finally, when I divide, I get 4. So it becomes 4x minus 12. If I change the sign, negative, positive, the remainder as I expected is 0. So what does it mean? It means now that this expression is equal to this multiplied by that. So let me write it down. So 2x to the 3 plus 3x squared minus 23x minus 12 is equal to x minus 3 times 2x squared plus 9x plus 4. Yes? So it means that if I put this back into this equation, let me make it a little bit smaller. If you go and replace this expression by this expression, you get closer to the factorization of your original problem one step more. Yes, so what I get is I will have 2 to the x4 plus 7x to the 3 minus 17x to the 2 minus 58x minus 24 is, I already had x plus 2 here, and instead of this expression I put this. So what I get is I have x plus 2, x minus 3, and then I have 2x squared plus 9x plus 4. Okay? But I might be able to factorize this one even more. Yes? And then of course here I want to use the tricks that we have already learned. Okay, let me write something here for you. about that polynomial. So 2x squared plus 9x plus 4. Do you remember how I did this in the previous sessions? This is a quadratic polynomial. There are many ways we learned to do this, but here I want to use this one that I multiply this by 2 and then divide by 2. So if you remember, I multiply everything by 2, so it becomes 4x squared plus 18x plus 8. Then I would give the rule of the common term to 2x to the power of 2. Then I will have 9 times 2x plus 8. Yes? And then I would write 1 over 2. I will put 2x in 2 pairs of brackets, and I will ask myself, I need two numbers whose sum is positive 9 and the product is 8. It's very simple. It's plus 8 and plus 1. Yes? And now I multiply this 1/2 here inside, so the answer becomes simply x plus 4, and then I have 2x plus 1. And now finally, if I move this one and put it here, I will get my answer. So this becomes the fully factorized form of my expression. Yes, so I was able to factorize my polynomial into a product of 4 degree 1 polynomials. Yes, okay. Okay. So I would consider this actually a non-trivial problem. Don't you agree with me? So let us look at the whole solution here. So you see the solution was very lengthy, but it was doable. We were able to do it following a set of rules. Finding out the terms that I have to break out these terms so that by grouping them in an appropriate way I can factorize them is highly non-trivial in this case. But here we didn't guess. I want you to feel it, that we didn't guess anything. We were just following a set of rules, and at the end we were able to factorize this 4th degree polynomial. Yes? For example, if you just want to use the previous tricks that we learned in the previous lecture, for example, assume that you want to factorize this polynomial and reach to this answer. Now, if you remember, I told you a trick. Now that you have this in front of your eyes, you can find the appropriate ones. Yes? So you see here, 7x3, you find it here. But 7x3 is now written in terms of 4x3 plus 3x3. So this means that you need to break this. So let me write it here, by the way, for you. So if you want to use the same trick to solve this one, you need to break this into 4x3 plus 3x3. Okay, now let us go to the next one. What is the next one? It's negative 17x squared. Negative 17x squared is here. Here you have positive 6x squared, and here you have minus 23x squared. So you see, it's highly non-trivial. If you wanted to do this in the other way around, you need to break it into this form. You need to write it as 6x squared minus 23x squared, which I agree, I hope that you agree this is very non-trivial to guess. Okay? And then this minus 58x, if you find it here, you need to write it as minus 46 minus 12x. Yes, so you need to write this one minus 46x minus 12x. So you see that this is really non-trivial, that I need to divide, to decompose these terms into these 3 terms. And then if you were able to guess, of course, exact numbers like this, I would say that you could solve it easier. I really recommend you to do it yourself after the video. If this lesson is finished, try to factorize this polynomial using this trick here. Yes. And then of course you will get just up to here, and then you can use the more or less the same trick here, by looking at this long division, you can realize immediately how you should break these terms in order to be able to continue. But the reason that I am now able to guess this is not because I actually was able to see everything immediately and try to write this. The reason was that I have this long division in front of my eyes. Yes? So I hope that you realized what is going on, even though this problem was very lengthy. The reason is that this was highly non-trivial and we were able to solve the problem without even guessing even one single number. Yes. Okay, good. Now I go to the next problem. Let me read this remark. This is important. You might think if a polynomial with integer coefficients does not have any integer roots, then it cannot be factorized. Or at least it cannot be factorized over the set of integers. But none of them is indeed true. Let us consider an example. Here, in this example, I have a polynomial with integer coefficients. Okay? First, I want to show that this polynomial does not have any integer roots. I can do it in two ways. The old method, because this is a quadratic equation, I can simply solve it and see what are the roots, and then see that if the roots are integer or not. So let us do this way, the old way. So I put 6x squared plus 7x plus 2 equals to 0. What I get using ABC formula, it's minus 7 plus and minus square root of 7 to the 2 minus 4 times 6 times 2 divided by 2 times 6. So it's minus 7 plus and minus, this is 49 minus 48, which is 1, and then I have 12. So you see that I have two roots. So one root is equal to minus 7 minus 1 divided by 12. It's minus 8 over 12. It's minus 2 over 3. And the other one is what? Minus 7 plus 1 is minus 6 over 12, or minus 1 half. So you see minus 2 over 3 does not belong to the set of integers. Minus 1 over 2 does not belong to the set of integers. By the way, using the method that we just learned as a theorem here today, we can also solve this problem in a different way. According to the previous theorem, if this polynomial with integer coefficients is supposed to have an integer root, that integer root should be among the integer factors of 2. But what are the integer factors of 2? Factors of 2 are plus and minus 1, plus and minus 2. So it means that if this polynomial is supposed to have an integer root, it should be between these four numbers. But this is a matter of just checking, very simple checking, that none of these are indeed a root of that polynomial. For example, if I put 1 here, this becomes 6 plus 7 plus 2, which is not 0. If I put minus 1 here, it becomes 6 minus 7 plus 2, here not 0. And you can easily check that this will not happen if I put plus or minus 2. So this is also one other way to show that there are no integer roots for this. Okay, now you see the part 2 of the problem, despite the fact that p of x does not have any integer roots, show that it can still be factorized over the set of integers. This is the crucial point that I wanted to mention it. You might think that because the roots are fractions, because the roots are rationals, not integers, then there is no hope that this polynomial can be factorized on the set of integers. But this is a wrong impression, because you immediately see that this is doable in this case. Why? Do you remember? I told you a formula in one of the previous lectures that if I have ax squared plus bx plus c, I can write it as a times x minus x1 times x minus x2, where x1 and x2 are the roots of that quadratic equation. I know my roots here now, so let me use the formula. So 6x squared plus 7x plus 2 is equal to, instead of a, I put 6, so this becomes 6, and then I have x here and x here, minus x1, so it becomes minus 2 over 3, minus 1 over 2. Yes, so this is my x1, I put it here, and this is my x2, I put it here. But I can simplify that. Instead of 6, I can write 2 times 3, and then it becomes x plus 2/3, and then x plus 1/2, and then I decide, you see, I can multiply these two in the last pairs of brackets, and then this one in the first one. And then you see, in this form, this is not factorized on the set of integers because the roots are fractions. But because of this extra factor that I have outside, it is still possible to factorize the polynomial on the set of integers. Yes, because after I did this multiplication, I will multiply 2 here, and I will multiply 3 in this bracket. So this 3 that will go in, it becomes 3x. Here it becomes 3x, and then I have 3 times 2/3. This 3 and 3 are gone. So the answer is 3x plus 2, and the next pair of brackets becomes 2x plus 1, and I have it here. So you see that this is a very simple example. This was a polynomial with integer coefficients. The roots, none of the roots of this polynomial is an integer. This polynomial has 2 roots. None of them are integers. None of them is an integer. But then I was able to factorize this on the set of integers. Why? Because the numbers involved now, all of them are integers. So this factorization is done over the set of integers, even though the roots were not integers. So this is a tricky point, so you need to know about that. Okay? Okay, so now let us go to the next page. So this remark was actually what I described on the previous page. So it might be possible to factorize a polynomial with integer coefficients over the set of integers, even if the polynomial has only non-integer rational roots. Yes, you see, this was a polynomial with integer roots, with integer coefficients, and with rational numbers as the roots that are not integers. But still, we were able to factorize it over the set of integers because the numbers at the end are all integers. Yes, so but I want to extend our previous theorem to a more complete one, but I need to define a notion for you first, and that is the notion of co-prime integers. Two non-zero integers p and q are said to be co-prime if the only common positive factor of them is 1. So co-prime numbers are sometimes called relatively prime or mutually prime integers. So let me give a very simple example. So by the way, don't mix this term with the notion of a prime number. It becomes clear in this example. Consider integers 6 and 35. First of all, you see that none of them are prime numbers. 6 is not a prime number. 35 is not a prime number. But we say that these numbers are relatively prime. Or we say that these are co-primes. What does it mean? It means that if you find the positive factors of 6, they are 1, 2, 3, and 6. And if you find the positive factor of 35, they are 1, 5, and 7. And if you see this list and this list, there is only one number in common, and that is 1. So we say that the 1 is the only positive common factor. So based on this definition, these numbers are coprimes. And then another word, we say that they are relatively prime. It doesn't mean that they are prime. On the other hand, 35 and 42 are not coprime. Why? Because 7 is a factor of 35, it's also a factor of 42. So in the list of factors of 35 and the list of factors of 42, I was able to find another factor except a factor except one that is common to both of them, and that is 7. Yes, so that's the meaning of being coprime. Now let us go to a little bit harder theorem here. So it's more or less an extension of the previous theorem. We have the polynomial. Again, my polynomial has integer coefficients. Yes, so let p of x, this polynomial, be a polynomial with integer coefficients. So all these numbers, all these a's are integer numbers. This time, if a rational number, a fraction s over t, if this rational number where s and t are co-prime integers is a root of p of x, then s, which is the numerator, is a factor of a0, the constant term, and t, which is the denominator, is a factor of an, the leading term. Yes, so what I'm trying to say is this. Let me describe it simply. So if in this polynomial, if p of s over t is 0, I want to prove that s is a factor of a0 and t is a factor of an. This is what we want to prove. Okay, so let us start from here. P of s over t is equal to 0. So what does it mean? It means that if I replace these x's in my polynomial with this number, the answer is supposed to be equal to 0. So let us write it down. So this means that an s over t to power n plus a sub n minus 1 s over t to power n minus 1 a n sub n minus 2 s over t to power n minus 2, and then if I continue, a2 s over t to power 2, a1 s over t plus a0 is equal to 0. Yes, but then let me quickly simplify this. You know that every fraction to some power, I can raise the numerator to that power and the denominator to that power. So let me just do it quickly. And I don't really need to write all the terms again. So let me just keep 2 terms. Yes. Okay. Now I want to get rid of all fractions. I don't want to get rid of all these fractions. So what I do, I multiply everything by t to the n. If I multiply this by t to the n, then this is gone. I will get a n s n. But if I multiply this by tn, tn minus 1 and tn will be simplified, then I will get a t. So t will be multiplied by this. And then I will continue, okay? So if I do that, it becomes an sn The next term becomes an minus 1 t sn minus 1. The next term, I continue. If I multiply this by tn, t2 and tn will be simplified, tn minus 2 will be left, and then I have s2. So this becomes a2 tn minus 2 and s2, and then I will have a1 tn minus 1 s, and then I will have a tn a0. Or let me write a0 tn. But on the right hand side, tn times 0 is again 0. Okay, so we can interpret this in two different ways now. Okay, we can take between these terms, I can take s out. Okay, so I will have s, and then I will have an s to the n minus 1 plus an minus 1 times t s to the power of n minus 2, and I will continue until a2 t to the power of minus 2 n minus 2 and then times s plus a1 t to the power of n minus 1, and then I close it, and then I put a0 tn here at the end, and then I will have 0. This is one way of interpreting this. Or we can conclude another thing. Instead of factoring s out, I will consider these terms, not this done. From here to here, I factor t out. Yes, so then what happens? I would write this term as it is. So it is an sn. But what I do, I factor a t out between all these terms. You see, all of them have a factor at least of 1t. I factor that t out. Then it becomes an minus 1. Then I will have sn minus 1. This will continue. This will give me a2 t to the power of n minus 3 s. And then I will have a t to the power of n minus 2s plus a0 t to the power of n minus 1 and equals to 0. So if you want to check I have done everything correct, try to multiply this back. Yes, you will get all those terms. Let us check. If I multiply this by this, it will give me exactly this term. If I continue, if I multiply this by that, t to power 1, t to power n minus 3. If I multiply them, it becomes t to the power of n minus 3 plus 1, which is n minus 2, and that's exactly what you see here. Yes. Okay, so I realized that I made a mistake. There is a power of 2 that I have missed here. Yes, that's correct. But now, what is important here is this. Okay, so unfortunately I don't have enough space here, so if you don't mind, let me take these two with me to the next. Let me take them one by one. So yeah, let me take this one first with me to the next page. Yes. Okay, so this is one of those results that I got here. But if you remember, A's are all integers, and if you remember, S and T were also integers. So this is immediately seen to be an integer number. It belongs to the set of integers. So let me give it a name, yes. For example, let me call this K. So then it becomes S times capital K. Let me call this one, this expression, I will call it capital K. Then I will have plus a0 t to the power of n equals to 0. Yes. So what I can conclude from here is that Sk is equal to a0 negative a0 t to the power of n. Okay, so what does it mean? It means that S here is a factor of this expression. Why? Because S multiplied by an integer gives this integer. So this means that S itself is a factor of this. Yes. So then this means that A0 Tn is divisible. Let me write it the other way around. So this means that S is a factor of A0 Tn. It's a factor, of course, of minus A0 Tn, but if this is a factor of minus A0 Tn, this is also a factor of A0 Tn itself. But do you remember we had this rule that S and T are coprime? Okay, so it means that there is no common term, there is no common factor between S and T. And if there is no common factor between S and T, it doesn't matter if I raise T to power n. Okay, so what I'm saying is that if S and T are coprime, so what does it mean? It means that there is no common factor between S and T except 1. Then immediately you can see that S and T to power n are also coprime. So it means that there is no common factor between S and T to power n. Yes? So it means that S that is a factor of this, it cannot be a factor of Tn, so it has to be a factor of A0. So therefore, S is a factor of A0. Yes, and that was one part of the problem. So I leave the other part as the exercise, so it's very, very similar. But this time you need to go here and concentrate here. Again, the same story. This is an integer, so for example, you can call it q, then you have ans to power n plus tq is equal to 0. And you have exactly the same line of argument. With the same line of argument, you can follow that. This time, t is a factor of the leading term an. Okay, so the crucial point here is this one, that if these two are coprimes, s and t to the power of n are also coprimes, but this is clear. Let me repeat it. S and t are coprime. It means that the only common factor between S and T is 1. So it is not possible to have a new common factor between S and T to the power of n, because the factors involved in T to power n, the prime factors involved in T to power n, are exactly the same prime factors that are involved in T. And S doesn't have any of those prime numbers as a factor. So it means that S will not have any of those prime numbers even in this number t to the n. So it means that S and Tn are coprime numbers as well. So then by looking here, you see that S is already a factor of A0 Tn, but S cannot have any factor in common with t to the power of n. So there is only one way that S can be a factor of this. And this happens if and only if S is a factor of this part, which is A0. Okay. Okay. Now let us go to the next problem. Let's see how we can actually solve the next problem. Again, the problem is factorize this polynomial. Yes. So if I want to factorize this polynomial, the first thing that I do, if you remember, is to try to look for an integer solution, integer root for this polynomial. So I would write the factors of -2 first, factors of -2. Then I will get plus or -1, plus or -2. Yes, but I have already checked them. So if you put all of these numbers here, you will not get 0. You will not get 0 here. Okay, so this means that this polynomial doesn't have any integer solutions. But still it might have a rational solution, which is not integer. But this is also good, yes, because let me again go back and remind you about this. You see, this polynomial doesn't have any integer root, but still it was possible to factorize this over the set of integers. Yes, so okay, this is still might be the case for this one as well. So now I use the theorem. Is it possible for this polynomial to have rational roots? Yes, if that's the case, if that is the case, when we have this theorem, yes, this theorem tells you that if a polynomial wants to have a rational root, then the numerator should be a factor of the constant term, and the denominator should be a factor of the leading term. Okay, so we already know the factors of the constant term. That was my constant term, and I listed my factors, and I told you that none of them will work here. You can check it yourself. And then what I need to write are the factors of my leading term. Factors, my leading term here is 6. So the factors of 6 are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. So this is so this will play the role of the s, the numerator. This will play the role of t. So how many different possibilities can I have now? Okay, if I divide this by that, the answers are plus or minus 1, but I already know that plus and minus 1 are not answers. So the other possibility is that I divide this by this. So one candidate is plus minus 1 divided by plus minus 2 is plus or minus 1/2. This is one candidate. So let me write rational roots. Possible rational roots, yes. Possible rational roots. The candidates that I have are plus or minus 1/2. Yes. The other possibility is that I take this one with that one. It gives me, I divide s by t. It gives me plus or minus 1/3. And then I divide plus or minus 1 over this one. I will have another candidate, plus or minus 1/6. And then I go here with this one. If I divide this by this one, it will give me plus or minus 2. But plus or minus 2, I already excluded them. If I divide this by this, it will give me plus or minus 1, but I have already excluded that. So I divide this by that, it will give me plus or minus 2/3. And then if I divide this by this, it will give me plus or minus 2/6, which is plus or minus 1/3, but I have already this in my list. So these are the only possible candidates that I will have. If this polynomial is going to have a rational root which is not an integer. Okay, so then you need to start to check. Yes, for example, I can start putting 1/2 here. So if you put 1/2 here, so it becomes 6 over 2 to the power of 4 plus minus 5 divided by 2 to the power of 3 plus 3 to the power divided by 2 to the power of 2 plus 3 over, so sorry, let me double check. I am putting minus a half here. I am checking minus a half. If I put minus a half here, this becomes positive. This becomes negative, yes. This becomes positive. And then the next one also becomes positive, and then I have minus 2. So what I have done, I have put minus a half. I'm just checking them one by one. I put minus a half here instead of x, here, here, and here. This is the answer. So let us calculate this. 6 divided by 16, which is 3 divided by 8, minus 5 divided by 8, and then I have 3 over 4, and then I have 3 over 2, and that's minus 2. So this becomes minus 2 over 8. This is minus 2 over 8, which is minus 1 over 4. And this becomes 1 over 2. Yeah, that's 0. So this number is 0. So yes, I was lucky actually. So minus a 1/2 is actually a root for this polynomial. So what I got, let me write it here. I got that p of minus a half is 0. So what I can conclude is that p of x is divisible by x minus minus a half, which is x plus 1/2. Okay, so I can use the long division method again. So I would write 6x to the 4 plus 5x to the 3 plus 3x to the 2 minus 3x minus 2. And then I do the long division, but this time I divide by x plus a half. Yes, so let me change the color. So I divide 6x4 by x, it becomes 6x to the 3, then I multiply this back, it becomes 6x to the 4, and then I will have positive. If I multiply 6x to the 3 by 1/2, it becomes 3x to the 3, so it becomes 3x to the 3. Then I will change the sign as usual. Then if I add them, this is gone, and this one with that one gives me 2x3. And I will bring down the rest as it is, yes. And now I repeat the process. 2x to the 3 divided by x is 2x squared. Then I multiply 2x squared there, it becomes 2x cubed plus x squared, yes. I multiply this by 1/2, it gives me plus x squared. So I will change the sign, this becomes negative, this becomes negative, and then I add them. Then this time it's gone, and then minus x squared plus 3x squared is 2x squared minus 3x minus 2, and I repeat the process. So this becomes 2x. I multiply this, it becomes 2x squared plus x. I change the signs and I add them, they are gone. So then it becomes minus 4x minus 2, and finally if I divide one more, it becomes minus 4x minus 2. If I change the sign, I add them, and I expected to get the 0 as the denominator, but what happens is I write that the dividend is equal to the divisor multiplied by the quotient, and plus the remainder. Of course the remainder is 0. So what I get is that 6x to the 4 plus 5x to the 3 plus 3x squared minus 3x minus 2 is equal to x plus a half multiplied by 6x to the 3 plus 2x squared plus 2x minus 4. You see, you might wonder that this is not valid because this is a fraction and it's not an integer. And I always tell you that by default, and of course it is mentioned that we are supposed to factorize on the set of integers. And even if they don't mention, by default we always mean that we want to factorize on the set of integers, over the set of integers. But this is not an obstacle, you see, because this one happens to have a factor of 2. So then I can factor that 1 out, so it becomes x plus 1/2. I factor a 2 out from here, this becomes 3x to the 3 plus x squared plus x minus 2. But then what happens, I can use this 2 and multiply it here, then I will get rid of this fraction. So still everything is okay. At least I was able to factorize it on the set of integers. Okay, so far I got this. So let me put this in a box. So I got this for this is valid, yes, because you see all the numbers involved now as coefficients are all integers. And this is a product. I wrote this expression as a product. So far I would say that I succeeded in factorizing this. But it might not be complete yet. I need to check this one again from scratch. I should do the same process for this problem. Yes. Of course, I don't need to check the integer roots, but then the idea is that because if this is going to have an integer root, it means that the original one should also have an integer root. Any root of this is also a root of that. So you don't need to check these integer values, but you need to check these fractional values. So again, I will repeat the process for this one. Okay, so what I do, I would write factors of this expression, of this number, factors of -2. What are they? As before, plus and minus 1, plus and minus 2. And then this time I will take the factors of 3 this time. So factors of 3, they are plus and minus 1, plus and minus 3. And then I look at the fractions. This will play the role of s, this will play the role of t. If I divide this by this, it becomes plus or minus 1. I don't need it. If I divide this by this, yes, that's a candidate, so it becomes plus or minus 1 over 3. If I divide this by this, it doesn't work because it becomes plus and minus 2, which is not actually acceptable in this case. And then I divide this by this, I will have 2 more candidates, plus or minus 2/3. So these are the possible rational roots. Okay, it's not clear that they are the roots. If these are not the roots of this polynomial, it means that this polynomial cannot be factorized over the set of rational numbers. And if it is not possible to factorize it on the set of rational numbers, we cannot factorize it on the set of integers. So it means that this would be the end of the problem here. But let us check. So let us do all of them. So here, if I check 1/3 here, so 1/3 so 1/3 doesn't work here, so you can check it yourself. Put 1/3 instead of x, and you will see that this is not 0. Yes. Yeah, it is not equal to 0. And if I put minus 1/3, this doesn't work either. But let us check these two numbers. So yes, let me check this number. So let us put 3. Then I have 2/3 to the power of 3 plus 2/3 to the power of 2 plus 2/3 minus 2. So this becomes 8/9. The other one is 4/9. The other one is 2/3 minus 2. So this becomes 12/9, which I simplify by 3. It becomes 4/3 plus 2/3 minus 2, 6/3 minus 2, which is 0. Yes. So 2/3 actually works. So let me take this one with me. So what I can conclude, let me give this a name. Let me call this one QX. Now we realize that q of 2 over 3 is 0. Now I understand that q of x is divisible by x minus 2/3. Yes? So if I go to the next page, let me take this with me. This is my qx. Hopefully I can just, no, it was not successful. So I can clean the rest that I don't need. Yes. So this is my qx. Yes. This is my qx. And then as I did it here, I know that this qx is divisible by x minus 2/3. Yes, so I go and do the long division here. So what can I do? I write 3x to the 3 plus x squared plus x minus 2, and then I divide it by x minus 2/3. Yes, x minus 2/3. So let me change the color. So again, I divide the first term by the first term. I will get 3x squared, and then if I multiply it, it becomes 3x cubed, and then I will have minus x squared. Minus 2x squared. If I multiply this by minus 2/3, it becomes minus 2x squared. I will change the signs, negative, positive, and then I add them. This is gone. This becomes positive 3x squared plus x minus 2. I divide once more. It becomes positive 3x squared minus 2x. Then I will change the signs, negative, positive. This is gone. I will get 3x minus 2. And if I divide, I will get positive 3. It becomes 3x minus 2. I will change the signs, negative, positive. Then the remainder becomes 0. So now what I get is this. What I get is that 3x to the 2 plus x to the 2, 3x to the 3 plus x to the 2 plus x minus 2 is equal to the product of this and that plus the remainder. The remainder is 0. So this becomes x minus 2/3 times 3x squared plus 3x plus 3. Again, you see that this is in principle not acceptable here because 2/3 is a rational number, but the good point here is that I have a factor of 3 all the way around. So I will factor that one out. I will get x squared plus x plus 1. Then I use this 3 and multiply it here. So then it becomes 3x minus 2, x squared plus x plus 1. Yes. So if you don't mind, let me go back and bring what I had before. So you see my polynomial, this one. So let me take this one with me to the next page. So here we had something like this here. So the polynomial that I was supposed to factorize was this polynomial. We succeeded to go so far, and then we realized this part itself can be factorized in this form. So finally what I write is that my original polynomial 6x to the 4 plus 5x to the 3 plus 3x to the 2 minus 3x minus 2 is equal to 2x plus 1. From the beginning I had it here, and instead of this I put this one. So then it becomes 3x minus 2, and then I have x squared plus x plus 1. Yes, and hopefully you have enough experience by now that you know that this is not factorizable. Why? Because, for example, the delta of this quadratic polynomial is negative. if you calculate the delta here, so it is 1 to the 2 minus 4 times 1, which is minus 3, and it's negative. So it means that this doesn't have any root. So if you, on the real set, so it means that if you want to factorize this, you can do it, but you have to go to the complex numbers. So this means that this is the end of the factorization of my polynomial on the set of integers. Yes, it was possible, even though this polynomial doesn't have any integer roots, but still we were able to factorize this on the set of integers. You see, all the numbers involved are integers. Okay? Okay. So I hope that this video was somehow useful. I spend many hours enthusiastically to make these videos available for free. If you found the video somehow useful and enjoyed watching it, I will be very happy if you could give me a thumb up. By subscribing to my channel, you will be immediately notified if I upload a video. Until the next video, be safe and goodbye. Thank you.